Okay.
Okay, so yeah, so let's begin from where we left. Special case of course, whatever I was trying to describe is the situation when we are working over real field, right? So we can think of F as R, and then I have vector space V over R of finite dimension, and finite dimension, let's say n. And usually when we have this, by fixing a coordinate, we can think of V to be Rn. And by fixing a basis V1, V2, Vn, we get Rn, right? And this is what something we always try to think of. And there is a very special situation we study here, and what is called Euclidean space. Euclidean space, which is nothing but uh, uh, a real vector space, uh, real vector space. That is we have a vector space V over R together with what we call inner product, right? So what is an inner product? So let's define what is an inner product. So this is definition of inner product. This will make sense when we have a real vector space, right? So I have V, a vector space over R, and if I have a map, let's say beta from V cross V to V, sorry, V cross V to R, satisfying is an inner product if it satisfies number one, beta is a symmetric bilinear form. Beta is a symmetric bilinear form, and more is that it is also positive definite. Okay, so what is the meaning of positive definite? Beta of V comma V is greater than 0 if V is not 0. I think non-degenerate follows, but for the sake of convenience, you can write beta is a symmetric non-degenerate here. Okay, so this means inner product is a special example of symmetric non-degenerate bilinear form. If you remember, I said that there are many possible symmetric bilinear forms over real space, but this is something special one. I mean, this has this extra property here. So it turns out, which can be proved actually, not very difficult to prove, which will prove maybe, is this that among all those, so uh, we saw earlier, uh, uh, any non-degenerate symmetric bilinear form can be written with respect to certain spatial basis, can be written as 1 1 1, then certain minus 1 minus 1 minus 1. But not all of these are going to be inner product space. Uh, this is inner product. Inner product if and only if uh, uh, all of them are 1, all of them on the diagonal are 1. No -1 appears there. Then it is an inner product. That is to say, the inner product, and if we try to find its matrix in diagonal form, will correspond to the identity matrix 1 1 1 1. Okay, so this is one of the very special situation. Why this is very special situation? There is a reason why, of course, inner product is very important, because inner product. So I'm not going to tell a lot about it, but just to recall, inner product gives rise to norm. Norm. So norm of any vector v is defined to be. So you take the inner product of v with itself, uh, and then you take square root, positive square root. So positive root. And you know that once I have norm, uh, which gives rise to a metric, right? Gives rise to a metric. Uh, and we all know how to define a distance function using this. That is why that particular symmetric bilinear form is very important, and this is what we study, and this is why this is called Euclidean space, because it is like an Euclidean metric on this. Which comes from something very algebraic, and that algebraic object is that particular symmetric bilinear form, which corresponds to all 1 1 1 on the diagonal. Right. In fact, the way we have defined a norm here to any, uh, in fact, uh, to any non-degenerate symmetric bilinear form, we can define what is called quadratic form. Quadratic form by Q of V is simply beta VV, right? We don't take here square root because this can be defined over any field, and we don't know whether for that field whether we can take square root. So we usually don't take here square root. Whereas when we are defining norm, we take a square root because we want to get the usual metric. Okay, so that's the difference. So you see that this is why we choose in this particular symmetric bilinear form on Rn, which gives rise to this inner product space. So now onwards, we can denote this. Either we'll call real inner product space. This will mean that I'm working with a vector space V, which is over R, with an inner product. Right. This inner product is basically going to be uh, the beta here, which I defined here. So this beta will be given a new notation, and this new notation will be basically this kind of symbol, which I am going to write now, because this is what is the traditional symbol for inner product. So this is basically that particular beta here. This what we have written here in this symbol. Or it's also called Euclidean space, or we'll simply call Euclidean space. right? Not to say that other spaces are not important, other symmetric bilinear form are not important. For example, if you take the bilinear form 1, 1, 1, minus 1, right? So this will give rise to, if I want to look at Q of any V, which is supposed to be uh, uh, beta of some vector VV. For this, I just need to compute X transpose the matrix of that X. So the matrix is, I'm taking this matrix A. If we compute this, you will see that I get x1 square plus x2 square plus x3 square minus x4 square, right? Because of this last one, minus 1 here. And this gives rise to what is called Lorentzian space, which appears in relativity, uh, which is important in physics. While studying relativity theory. In any case, all these quadratic forms also give rise to group, and they give rise to different orthogonal group. Okay, so they are important in themselves, and there are many orthogonal group, not just only one orthogonal group. The orthogonal group which will correspond to inner product space turns out to be compact. That's the only difference. Others are non-compact. Maybe I'll tell a little bit about it towards the end. That how we can think of this as a topological group and things like that. Okay, so you also know that there is something else also we call inner product space, something over complex, right? And uh, uh, with my experience, many of the undergrad textbooks try to combine two different kind of inner product spaces. One is this real inner product space. Another inner product space is more complex, where some kind of complex conjugation is involved, right? And it gets quite confusing. So that is why I decided to present two of them separately, and both of them I am presenting in more general avatar, more general version, and those things will turn out to be special case of this. These things are important if you want to study more maths, if you want to study group theory, or if you want to study algebraic groups, Lie groups, or something like that. So it's important to even to know all this stuff, and plus it will help you clarify if you had any confusion with that. So now what I'm going to define is uh, a slightly new topic, uh, and then we'll come back to see the two situations which we are going to work with. So, like we defined bilinear form, now I'm going to define what I call sesquilinear form. Sesquilinear form. Okay. So, to define anything, first I have to begin with a setup where I want to define and all this kind of stuff. So, what we do is that we begin with a field F, which is extension of another field K of degree 2. And suppose I have a field automorphism. So let's say sigma is a field automorphism of order 2 because it's degree 2. So it is order 2 and its fixed field is K. And this automorphism will simply denote by alpha going to alpha bar. You know, so the classic example of this situation will be F is complex number, K is real number, and this is complex conjugation, right? So we begin with a situation when I have a field F with an automorphism of degree 2. I mean, you need not write K. You can just say that I have field with an automorphism of order 2, right? So this will mean that sigma square is identity, which just simply says that alpha bar is just alpha. Okay. So now what we do is that we begin with a vector space V, a vector space of dimension n, over F. All right. And now I want to define sesquilinear form. So this is definition. So the definition is this, that a map H from V cross V to F is said to be sesquilinear if it's linear in the first coordinate, if number one, H of, let's say, alpha V1 comma V2, maybe I should write it in one go, alpha of V1 plus V2 comma some W is alpha H V1 comma W plus H V2 comma W. And it is bar linear, or what is called conjugate linear, in the second coordinate. So what happens in the second coordinate is that bar comes out. So if I take V comma, if I take alpha W1 plus W2 in the second coordinate, then when alpha comes out, it comes out with a bar. The bar is the value of alpha after applying sigma. Okay. So then it is V comma W1 here plus H of V comma W2. And as again, so this is the definition of sesquilinear form. And one can make a further definition that a sesquilinear form is said to be Hermitian. This will be a familiar word for many of you. Said to be Hermitian if it satisfies. So what happens when we change coordinate? H of V, W, change the coordinate, but when you change the coordinate, it changes with a bar, because these are supposed to be scalar in the field F. So when we change the coordinate, you will get the conjugate of that scalar, not the same scalar. Okay. So then this is a sesquilinear form. Now we can try to study abstractly what are all possible Hermitian form. So the first thing, of course, we would like to do, as we did earlier, is that try to associate a matrix to this. And what do we get? So let's do that. So we try to associate a matrix. So what I call matrix version. So all these definitions have matrix version, which we obtain after fixing a basis. So matrix version is this. So fix a basis of V. Let's say it is V1, V2, Vn. It's n-dimensional vector space. And now I have H given, H from V cross V to F. What we can do, we can associate a matrix. So the associated matrix is defined as follows. The associated matrix is, let's say, denoted by H, is supposed to be, I'll calculate H on Vi comma Vj, right? I'll calculate this. This is what is my matrix. And we can verify that uh, uh, then suppose I have V in V with associated coordinate x1, x2, xn, which is x, and suppose I have W in V with associated coordinate y1, y2, yn, which is y. Then using this matrix, I can calculate H. So H of V comma W will be taking X transpose, then putting the matrix H here, but here I have to have Y bar. Okay, let's verify this quickly. This is not difficult, so let us verify this. So HV, I can write the coordinates of V are xi. So this is xi vi. The coordinates of W are yj. So yj vj. This is equal to. Now this is supposed to be linear in the first coordinate. So the xi will come out as it is equal to 1 to n h of vi comma summation over j yj vj. But we see that in the second coordinate, yj bar will come out. So this is I equal to 1 to n. Now I have double sum, j equal to 1 to n, xi yj bar h of vi vj. So you see that this is the matrix of h, and you can calculate, you can compute this one here to verify that you get this answer exactly. So this is how we get the matrix of a Hermitian form. And once again, the question arises before going to the question of the base change. If you do base change, how the matrix changes. Before that, let's just make for formality, let's make the definition here that the form, when we say non-degenerate, as I said that we can reduce the problem where zeros can be gotten rid of. H is said to be non-degenerate if determinant of H is not zero. The similar definition as we had for bilinear form. And we can also compute and see that H is Hermitian what happens to the associated matrix? I have H, right? So remember the Hermitian is that H bar, right? So H is going to be H uh, H bar transpose, right? When we switch the coordinate, instead of H being H transpose, which is what is a symmetric bilinear form, here the second coordinate changes with the bar, so H bar. So this is the definition of Hermitian. This is the equivalent property, equivalent version of saying H is Hermitian in matrix form. You can verify this with the computations we have done earlier, right? So now the question again arises: what happens with the base change when we do base change? When you do base change or change of basis, right? Again, it will give rise to equivalence, similarity basically here. And one can, I'll leave this maybe as an exercise to figure out. This is a good exercise because we have done the exercise for bilinear forms, so you should be able to find what equivalence relation we get here. Exercise. What equivalence relation it gives rise to. This gives rise to. So it will give rise to equation on MNF. And what is the equivalence relation? Figure this out. Okay. And again, the question is to find out the equivalence classes, a nice representative of equivalence classes. And we want to find out, uh, nice representatives of equivalence classes. Right? This is what the question we asked. All right. Um, so the answer is much more tricky in this case, and I will give you answer for one particular situation. That particular situation is, of course, of the complex case. This is what we will be interested in. So the classic case we are interested in F equal to C, and sigma from C to C is the complex conjugation Z going to Z bar. Okay, and the field K will become R here. You know that. So the field K here will be R. So C is extension of R here. Okay, and let's write down the theorem classifying non-degenerate Hermitian forms over C with this setup where sigma is the complex conjugation. So the theorem will say that there exists a basis of V such that matrix of H is one of the following, or rather it is in the following form. It's very similar to what you saw for real symmetric bilinear form. It has certain number of pluses and then certain number of minuses. This is P pluses, and this is, let's say, Q of minuses, and P plus Q is of course equal to N. You can always do this. This is what the theorem says, that there are these many Hermitian forms over complex numbers. Okay, and once again, I mean, I'll come back to the. Let me maybe say right away here. Then, what is the inner product space? Inner product, or the complex inner product, or C. So, okay. So we have a vector space V over C, and we are usually this notation from V cross V to C is an inner product if number one, this is Hermitian form, meaning it is sesquilinear form and the bar symmetric basically. And in addition, we need some kind of positive definite property. So this is again V comma V is greater than 0 if V is not 0, right? So this is the extra property required here. And once again, it turns out that that in the classification written above, in the classification of Hermitian form, only one of them gives rise to inner product space. Inner product. Once again, why inner product is important? Because it gives rise to metric. It gives rise to some norm and it gives rise to metric. So inner product is important. And this is the one which is corresponding to identity matrix. Inner gives rise to inner product corresponding to identity. Yeah. So this is what happens. So often it is defined this way. I mean, the standard example of inner product is on Cn. So suppose I have V is Cn, then the inner product is defined on Cn. So Cn cross Cn to C by let's say I have this is Z1, Z2, Zn, and this is W1, W2, Wn. This is defined to be summation over Zi, Wi bar. And you can see that for this particular Hermitian form, so this is Hermitian form, you can directly verify it. You can see that the associated matrix, if I choose the standard basis, associated matrix will be the identity matrix, right? And we can always convert an inner product space to something looking like this, and we'll come to that slowly. Uh, 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 Before that, I want to define again a group associated to this before I move to that topic. As I said that I'm quite interested in groups. So again, let's understand what is the group associated to this. And those groups are important in themselves, and they are well studied and quite important everywhere, including in physics and other places. What is called a unitary group. So let's define what is an isometry group. So I will take more. I will take the general version. So I have vector space V over F, and F over K is degree 2, and sigma is an automorphism of F of degree 2. So sigma square is identity. Okay. And suppose I have H Hermitian form on V, which is non-degenerate, then we define a map T from V to V is an isometry, like earlier definition, is an isometry if it preserves this H, right? If if H of any TV TW is H of V comma W for all V comma W in V. And we can collect all isometries. So this is definition of unitary group. This is a definition of unitary group, which is if I so I'll denote it by U, V comma H is set of all those endomorphisms which preserve the form H. H of TD, TW is H of VW for all VW, right? So this is the unitary group. Once again, one can write the matrix version of this, but I will leave it for you to decide. Leave it for you to write. So maybe as an exercise, write matrix version of the unitary group. Another exercise is, of course, to verify that this is actually a group. Although I called it a unitary group, but this set is a group. This is another exercise. UVH is a group. Okay, so so now we come to our uh, uh, proper study of inner product space. Usually, what we do in undergraduate courses, and that is a topic which is also very widely applicable in many situations, including graph theory and physics and other places. So the these are the two examples we study. So when we say inner product space, then we have V is over real, and I have the inner product which I defined earlier. And the second situation is when V is over complex, I have this inner product space which comes from Hermitian form. So this is supposed to be coming from symmetric bilinear form, symmetric positive definite bilinear form, and this one is here supposed to be Hermitian form. Hermitian, again positive definite form. Right? So these are the two classic situations we study. We are going to study here. Of course, the general versions are studied, very well studied, and a lot of things are known, etc. But let's restrict ourselves to this situation because there are some nice theorems which can be proved in this situation, which may not be true in general if you look at the general setup. Um, so, what will be the associated groups here? So, let's keep these two things in mind. So, what are the isometric groups? Okay. So when we are thinking of the real situation, in real case, the isometric group is O, and it's simply because it in the real case, instead of like earlier I was writing O V with respect to this, in the real case it is simply denoted in classical notation. Simply it is denoted as ON, and I just said that there is always a basis which makes this identity. Okay. And with that definition in matrix version, let me write this. So there exists a basis so that matrix of this is identity. Hence, the orthogonal group ON in matrix form will be simply all those, we're writing X, all those X in Mn R, because we are working for R, such that X transpose matrix of the bilinear form. Here it is identity, so I don't need to write that. So this is the familiar definition of orthogonal group. Yeah? And what happens in complex case? In complex case, we denoted by unitary group. So it is U, V, and it's the Hermitian form. And this is also simply denoted as UN classically. I mean, in regular textbooks. And again, there exists, as I explained, there exists a basis so that matrix of this is identity. And hence, in matrix form, this unitary group, UN, is simply all those X in MNC. Remember, these matrices are over complex. So these are MNC such that X transpose the matrix of the form, which is identity. So I want right here. And then X bar is identity. I hope this is familiar definition to all of you. This is what the unitary is. Okay, so keep this in mind that the orthogonal group and unitary group, these are the two groups associated to this. And one can study all these kind of operators and things like that. This is what we are going to do. Yeah. So now I'm just going to prepare some background and we'll prove some major theorems tomorrow. So let me just sketch. Let me
Sir,
give some.
here
Yeah.
is one typo. X into X conjugate transpose is equals to identity.
Just a second. What X into?
X conjugate transpose is equals to identity.
The two things are same actually. So the way I have been writing, it will turn out to be X transpose X bar is identity, right?
Okay.
Let me check. Is this what it will turn out to be? Yeah, I think the way I have been writing, if you see my matrix form when I was calculating, it always came like X transpose matrix of the form in between, then X bar equal to identity. But
Oh,
let me quickly point out. So you are saying that, so my definition X transpose X bar equal to identity, and you are saying that I should have had X transpose bar equal to identity, right? So from here you'll see that X, like X bar is basically X transpose inverse, right? And from
right,
here also you can just put bar here, you'll get the same thing. And
right,
from here you put bar.
right.
So X bar, X transpose, identity bar is just identity. So the two things will turn out to be the same. So both
Okay, okay.
they are same, but I'm following my methodical thing. If you follow the method which I described you'll get this equation.
Okay, sir. Okay.
Okay, but two things are not different. But if you want to generalize, I mean, if you want to think of a more general version where the matrix of the form may not be identity, then your definition will have problem.
Okay.
Okay, so like for example, if the matrix of the form was some H, then my unitary group will turn out to be some X transpose H X bar equal to H.
H.
This
Okay.
equation, it will turn out to be this equation. If H is the matrix of H. Okay. So then
Okay, sir.
you might if you put transpose here, then this equation, I don't know whether they are same. They might be different even.
Okay, sir. I got your point. I'll
Yeah,
check myself again.
yeah. No, I know. I mean, that is how the definition is written in a linear algebra textbook. I mean, you are right. This is how the definition in linear algebra textbooks are written, especially the undergraduate textbooks. And
But for the general version, you are
yeah,
talking.
yeah. So I'm saying that, but if you want to study more generally, then that definition somehow doesn't match with the general definition. So
Oh,
although in this situation both are same.
thank you.
Yeah. So yeah. So the fact why I'm saying that there is this identity always here for real and complex inner product space. In general, together we'll call this inner product space. So inner product space, why they correspond, why there always exists a basis so that the matrix is orthogonal, matrix is identity. This is because there is always an orthogonal basis. In fact, there always exists an orthonormal basis. There exists an orthonormal basis. Whenever I have inner product space, this is a theorem. And what is that theorem? It is actually a name theorem. How did it follow? Anybody can tell me? Theorem is this. Yeah. Have you heard what is called gram orthogonalization process? So what does this process does? You can begin with any basis, and this process will convert that basis to an orthonormal basis. Okay, for inner product space. And that means an orthonormal basis always exists because there is always a basis, and that basis can be converted to an orthonormal basis by using this process. So there is always an orthonormal basis. And when you are orthonormal basis, with respect to that orthonormal basis, if you try to write the matrix of the bilinear form or Hermitian form, you will get identity matrix. Yeah. So the proof is very simple in this case of this fact, which I am saying that this is always identity matrix, but it's not as simple. If I want to prove the general version of the theorem where I said that any Hermitian form will look like some 1 1 1 and some minus 1 minus 1 minus 1. So the proof is more complicated. But if you just want to say the matrix of this inner product space corresponding Hermitian form is identity, then this is just gram orthogonalization process. Okay. Uh, uh, I want to say. Okay. So what do I want to say? Let me formally write some of these stuff as a definition so that we just recall. So when I have V comma this inner product space, it could mean one of the two. So this I will simply denote by inner product space. I'll just write IPS, inner product space, and it could be one of the two situations. Either real, when I have to say a particular situation, then I will say the real inner product space and complex inner product space. So these are the two of them which I said earlier. It could be over R or it could be over complex. Okay. So there are some theorems or some generality which holds true in both case, but there are some theorems which will come to later which may not be true in both cases. So there we will again need to distinguish which one is real, which one is complex. Uh, this is one of the confusing point what especially some of the linear algebra textbook try to do. They begin with this situation, and you later it becomes confusing that why something is happening over R, something is not happening over C, and things like that. But they begin with the two situations together. So what happens that first thing is that we can define here. So we say that V comma W, two vectors when V and W are orthogonal if V comma W is 0, right? And similarly, if I have W a subspace of V, we can define the perpendicular of W. So here also sometimes just notation we simply use V perpendicular to W, right? This kind of notations are used, so we can use them. And the perpendicular of W can be defined by set of all those vectors V in V, which are perpendicular to every element of W for all W and W. Right? And it's a exercise or lemma. Maybe I'll leave it as an exercise that if I take W a subspace of V, then I can write V as W direct sum W perpendicular. Uh, so this happens for the inner product spaces we have chosen, but this lemma may not be true if you are working with general version of symmetric bilinear form or Hermitian form, which I define. So this lemma is not true in more general, but this is certainly true for inner product spaces which we are working with here, right? Because after all, there cannot be any vector which is perpendicular to both W and its perpendicular which is complement. It will become perpendicular to everything in V, which is just 0. So okay, and then uh, then uh, then another some I mean, okay, let me just keep writing it as a fact rather than because I don't want to prove these things, and I assume that you have already know these things very easily, so I don't need to spend time on this. If I take orthogonal set of vectors, then they are linearly independent. Yeah? If I take any orthogonal set of vectors, they are always linearly independent. The next fact was what I already stated, Gram orthogonalization process. Process. This process begins with any basis v1, v2, vn, and converts it to uh, another basis. We can call it w1, w2, wn, which is orthonormal. And not in a random way. It is in such a way. This is important actually. It's part of the process that if you take subspace generated by v1, v2, vk, any k of them, it is actually equal to subspace generated by w1, w2, wk for all k between 1 to n. So this is just the process itself. Whatever you know, this is automatically, this is a part of that step. It's an algorithmic process, in fact, right? So these are things. Now I just want to give you an outline what we are planning to do tomorrow. So this is just outline for tomorrow. Okay. So we are going to prove some interesting theorems. The first theorem is uh, that uh, if I take a unitary operator, uh, let T be in UN, so that is unitary operator, then uh, uh, T is uh, diagonalizable. A similar theorem for real can be said, but it's not exactly diagonalizable, but it is a little more complicated. If I take something in ON, then uh, T can be represented, T can be made uh, like it can be made like, so there'll be some diagonal lambda 1 lambda 2 up to some lambda r, and then there'll be some 2 by 2 blocks. Okay, some 2 by 2 blocks. So it may not be just 1 by 1 block as happens in unitary group case, but in this case these are quite important theorems, and this will follow from what is called structure theory of normal operators. So structure theory of normal operators. We will define what is a normal operator. To define normal operator, we need to define adjoint. And so given T, there is a way to define what is adjoint of T. And normal is something uh, uh, T into T star is T star into T, right? And for such kind of operators, we will get some kind of structure theory. And this structure theory will lead to some interesting theorems. So this is the project. Uh, this is what we will do tomorrow. In fact, what is called spectral theorem for normal operators. Spectral theorem meaning like you can mostly diagonalize it, and that is what gives us those theorems. Anybody has any question? Otherwise, I just wanted to tell a little bit about some example of topological groups here. So if I think of, let's say, matrices, R by R, N by N matrices over real, right? Or we can also think of matrices over complex, right? So I can actually think of this as uh, N square coordinates, right? But if I think of something with N square coordinate, on this I can define inner product. On both I can have inner product, right? Or rather a metric. I can think of it as a metric space. So that way I can think of MNR and MNC both as metric space also, right? And then we have this kind of groups what we defined just now. Then we can have a subgroup which is GLN R, which is subgroup of MNR. This is metric space, but this need not be group. I'm thinking of this as additive, so I have to think of GLNR actually. So I'll think of GLNR, which is a group, but this is a subset of only that. Okay, let me correct this. should not say this. So GLNR as a subset of MNR gets metric topology. And it becomes a topological group. So it's a topological group. ONR is a subgroup of GLNR. So this will also become a topological group. There are many other groups you can define. For example, symplectic group, SPNR is also a subgroup of GLNR. So this will also become topological group. So you get many examples of topological groups. In fact, these are also examples of Lie group because there is a differentiability structure and all that. These are also example of algebraic groups. And similarly, of course, you can think of unitary group sitting inside GL and C, which will have a metric. So this is also example of topological group. And one can study these groups also using this kind of extra structure. So these groups are more structured basically. It has also topology, which is coming from metric. And sometimes those things are useful in proving theorems about these groups. One can study when, for example, like, as an exercise, one can try which of these groups are compact, which of the above groups are compact. These are good exercises to do, which of the above groups are compact or connected, simply connected or something like that. So this kind of, if you're interested, you can think about this kind of questions for these groups also. Yeah, I think I will stop here. If you have any question, you can ask me now. We have a few minutes. Anyone has any question?
Any questions from participants? If there are no questions, shall we end this session here, sir?
Yeah, okay. Yeah.
So
Thank
tomorrow
you.
we will meet at 4 p.m.
Tomorrow it is 4 p.m. Okay. Okay, good.
From 4 to 5. One
Okay.
lecture.
Yeah.
That will be followed by 2-hour tutorial. Tutorial will start at 5:15.
Okay.
Okay. So, okay. Thank you, sir. Thank you very
Okay.
much.
Thank you. Thank you,
Thanks
everyone.
everyone for joining this lecture. Bye. See you tomorrow at 4.
Okay, ma'am.
Bye.